remember Genique? Or next, previously in the previous class we have seen how the electric field will be varying in the charged sphere. Okay, how the electric field is varying inside the charged sphere and what will be the electric field outside the charged sphere. Okay, the electric field will be linearly increasing within the sphere, charged sphere. Now electric field will be decays non-linearly, okay, outside the sphere. Now in the previous problem it was given that it is just a charged sphere. It is just a charged sphere. Suppose if that sphere is in the given the same sphere, the same question, but in the same question the question was given as it is a conducting sphere. It is a conducting sphere of radius r, conducting sphere of radius r having charge density rho v, okay, charge density rho v, okay, write this one as a conducting sphere of charge density of radius r having a charge density rho v, okay. The question here is, okay, in the previous one is the charge sphere. No, right. The question is the E field of a conducting sphere of radius r having a charge density rho v inside, outside and on the surface is dash. Okay, on the surface is dash. Okay, you have to find the electric field intensity of a conducting sphere of r having a charge density rho v inside, outside and on the surface of the sphere is dash. Okay, so that is the thing. In the previous case it was just a charged sphere, but it is a conducting sphere. What happens and what will be the results of the electric field? Okay, so if you observe in the previous question, it was a sphere of radius r and it is conducting now. Now previously it was a charged sphere, but it is a conducting sphere. Conducting sphere. Okay. So whenever this is conducting means the charge particles will be here. What happens? The charge particles will be here plus. Let us suppose the charge particles are there means. So what happens? Here the charge particles, what happens? Before that there was a charge of rho v, charge density. What happens? The charge will be what happens? Whenever there is a conducting means what happens? If there is a conduction, what happens to this? All the charge carriers will repel. All the charge carriers will repel and they try to come out of this surface. Okay. So after repulsion, they try to come out of this surface. So what happens? All the surfaces will be come out. All the charge carriers will come out of this surface. Okay, so this is the thing you have to notice. So if all the charge carriers will come out of the surface, what happens? There will not be any charge within the surface. You have to notice this. This is one of the important and unknown thing most of the people, for the most of the people. Okay, most of the people don't know the difference between the conducting sphere and the charged sphere, but it is a conducting. So because of this conduction, what happens? The charge carriers will come out of this, like this. The charge carriers will come out of this surface, means all the charge carriers will come on to the surface of the sphere. Okay, so what happens now? Let us suppose it is having charge density rho v and charge q. Okay, charge density rho v and charge q. Let us suppose, let the q is the total charge. The q be the, let the q is the total charge on the sphere. Now what we have to find? So the total charge is reached onto the surface now. The total charge is reached onto the surface. Okay, so now what happens? So now suppose if you want to find the electric field intensity inside this, suppose if you want to find the electric field intensity at any distance from the center of this sphere, what happens? So this is the Gaussian surface. The closed integral d dot ds is equals to q enclosed. So what is closed integral? I want to find the electric field intensity on this surface. Okay, so this is called as the Gaussian surface. So within this Gaussian surface, the total flux coming out of this surface equals to the total charge enclosed in the volume. So what is the total charge enclosed in the volume? Enclosed in the volume. Okay, what happens? It is 0. There is no charge inside this. So there is no charge inside this means it is 0. The charge enclosed within this is 0 because all the charge is vacated. All the sphere is vacated. Okay, all the charge is reached onto the surface of the sphere. So from this d into ds, integral ds is equals to 0. So from this d is equals to 0. So from this e is equals to 0. And this is very, very important for the conducting sphere. E is 0 and d is 0 inside. This is what? This is for r less than r. Okay. What is the second one? If r is greater than r, what happens? If r greater than r. What if r greater than r? Smaller greater than r means outside. So outside means I have to consider this Gaussian surface now. I want to find the electric field intensity at this r. Before this it was this one r. Now this is the r smaller. Now so consider this Gaussian surface. So closed integral d dot ds is equals to charge enclosed in the volume. What is the charge enclosed? The total charge. I said that I assume that the total charge is q now. Okay. The total charge. What is the total charge within this volume? What is the total charge within this volume? The total charge is this one only. The total charge is accumulated. The total charge is reached to the surface of the sphere. So this is equivalent to what? It is q. So d, because the d is same everywhere on this Gaussian surface. So d into integral ds is 4 pi small r square. What is the small r square? It is the radius. So on this surface, the d is same. So I have to take this Gaussian surface area. So this is this one. So d is equals to q divided by 4 pi r square. It is just like what? It is the electric field intensity due to the point charge. Okay, so this is D. So what about E? E is equals to Q divided by 4 pi R square. Okay, so this is, it's a conducting sphere. The charge is conducting on this. Okay, now observe this. This is Q divided by 4 pi R square at this point. Now what if it is the third case? At R is equals to capital R, what happens? So this is outside and this is inside. Inside up to this, what happens? It is 0. And at here, what I can write? Suppose if I consider this one as the Gaussian surface. Understand? So I have to consider where I have to calculate. I have to calculate the electric field intensity on the surface. So on the surface, I consider one Gaussian surface. Okay, I consider just Gaussian surface. So on the surface, I can include the charges. Okay, I can include the charges. Understand? So that's why, what is the charge now? On the surface, the charge is present. Okay, so closed integral d dot ds. Charge enclosed. What is the charge enclosed on this? What is the closed surface here? The D is same everywhere on this surface. Okay, on this spherical surface, the D is same into ds. ds is 4 pi capital R square. Why capital R square? I consider the Gaussian sphere as this one only, the original sphere. This is equal to, what is the charge on the surface? The charge on the surface is Q only. So now what is D? D is equals to Q divided by 4 pi R square. So what is E is equals to? E is equals to, so from this, what is E is equals to? E is equals to Q divided by 4 pi epsilon capital R square. So this is for what? R is equals to R. So like this, we have to apply. See, what is the difference between these three? It is R less than. Inside there is no electric field because it is conducting. The charge, entire charge is going to the surface of the sphere. In the previous problem, we solved that it was not a 0. But here, after this, it is just like a point charge expression. And here, it is also just like point charge expression. But here, we have to replace this R divided by this capital R. Okay. So, this is the total charge on the surface. That is the total electric field on the surface. So, this question is equally, this question will give equal result for, this question will give equal result for, okay, for conducting sphere or the shell. Okay, shell means it's a hollow, sphere means it is a solid sphere. Okay, so this, suppose in the question he has given sphere or shell, the result is same. Okay, suppose it is not a conducting, means it is for the previous question, already we solved it. These are the real applications of the Gauss law. Okay, so now how can we write, how can we draw the figure here? We can draw the figure as we drawn the figure for the previous question. So what is the figure for this? The relation between E and R. Let us suppose this is R. Let us suppose this is E. Okay. So what happens? So from when E is up to R, what happens? So inside the sphere. So R less than R means what we are getting? This is for R less than R. It is small r less than R. Right? So now, so inside the sphere what happens? there is the electric field is 0. Okay, but at R what we got? Q divided by 4 pi R square. So here we got Q divided by 4 pi R square. This is somewhere. Okay. Okay. So now what about this? And after R greater than R, it is as this is all is constant, but here R square, as R increases, it decreases. So this is the figure. And some people will write like this also. There is a suddenly before that it is 0. Suddenly when R reaches, it goes to an abrupt change. Q divided by 4 pi epsilon R square is the electric field. So like this. This is the figure for the electric field intensity versus the radius, the distance for the conducting shell or the conducting sphere of radius capital R. So this is the way to approach the Gauss law. Okay. The second application of the Gauss law. This is one more application. The application is the electric field intensity due to a line charge. The electric field intensity due to the line charge. So how can you find the electric field intensity due to the line charge? Okay. So now if you observe this, line charge is represented with what? It is rho L coulomb per meter square, rho L coulomb per meter. Okay, it is rho L. It is represented with rho L. Understand? So now let us suppose there is a line charge is placed on z-axis. There is a line charge is placed on the z-axis. It is from minus infinity to plus infinity. Okay, it is a line charge of rho L. It is a line charge of rho L coulomb per meter. It's okay. Due to a line charge. Which line charge? Due to an infinite line charge. The electric field intensity due to an infinite line charge of rho L coulomb per meter. Okay. So it is having an infinite line charge. It is placed along z-axis. So why I have chosen the z-axis means it is easy for me to apply the cylindrical coordinates. So that's why I placed this total line charge. So due to this line charge, I have to find the electric field intensity. So that's why with respect to this, I have to find the electric field intensity. So that's why I placed this one as the reference. And I put it on the reference line z-axis. Okay. Suppose if I want to find the electric field intensity at any point P, what happens? Already I said what we have to find. We have to consider one cylinder on which the point is presenting, where we have to find the electric field intensity presenting. Already we know this is what this represents a rho. Okay, why rho? The distance from the point, the distance to the point from the reference line is nothing but what? It is a rho. Okay. So now What we have to find? We have to find the electric field intensity by using this Gauss law. Okay, so what is the Gauss law is saying? So closed integral d dot ds is equals to charge enclosed or q enclosed. Okay, let us suppose, what is this length of this line? This length of this line is infinite. Okay, this length of this line is infinite. Let us suppose the length is represented with h tends to 0. H tends to infinity, sorry. H tends to infinity. Let us suppose L or length. The length is represented with h here. The length of this line tends to infinity. Okay. So now we have to use the Gauss law here. See, because rho is constant in all directions, what can? If this is rho, this is also rho. This is also rho. This is rho means this is rho, this is rho, this is rho. Okay. So if this is rho means what? It is also rho. It is also rho. It is also rho. It is also rho. Like this. All are rhos. So because it is equidistant from the see, that means on this surface you will be getting the same strength. The D is same everywhere. The rho is constant. Rho is constant means what? The ds will be in the direction of arrow. Okay, rho is constant means what? What we can write? So from this, D is same everywhere. D is also constant everywhere on the cylinder. So from this, what can I write? I can write this outside. So D closed integral ds can be equals to the charge enclosed. The charge enclosed. What is the charge enclosed? The charge enclosed is equals to what? The charge enclosed is equals to what is the charge? But it is given as a line charge. Okay. Suppose if I multiply the line charge with the length, then I will get the charge enclosed. So what is the length of this? Infinity, but I am taking this one as h. Okay, so that means I can write rho l into h. So it is d here. It is d here. What is integral ds? The integral ds is what? The integral ds is what? S. S means the surface area of this cylinder. I consider this Gaussian surface as the cylinder. So what is the surface area of the cylinder? Cylinder surface area is 2 pi rho h. 2 pi RH or 2 pi rho h, where rho is the radius of the cylinder. So from this, D is equals to h will get cancelled. Why I have taken h means it is also infinity, it is also infinity. So you will get indeterminate form. So that's why I have taken this h tends to infinity there. Okay. So here you will get rho l divided by 2 pi rho. Now what will be the direction? Because it is rho constant surface, the surface, here is the surface, right? So that means already we know the electric field will be in the arrow direction, radially outward. The electric field will be radially outward. It is arrow. Then what about the electric field intensity? Due to electric field intensity E, the E is equals to what? E is equals to d by epsilon rho l divided by 2 pi epsilon rho arrow. So this is a very important result. Then how the electric field will be? The electric field will be in the arrow direction. So that means if this is a line charge, the electric field will be in this direction. The electric field will be in this direction. Everywhere Okay, it is like a brush for washing the bottles, water bottles, right? It is like a brush. Okay, so the brush will be looking like, in between there will be a reference axis. Okay, so the brush will be it is looking like the brush which is washed for the bottles. Okay, which is used for washing bottles. Okay, so now, so this is the electric field intensity. So it is, the E field is radially outward from the cause. What is the cause here? It is rho L. Similarly, how can we find the, it is the Gauss law application. This is for the what? Electric field. Suppose if you want to find the same kind of cause in the magnetic field, what? The second one is what? H field. The magnetic field intensity due to the infinite length current I carrying wire. Similar to this, what I have to find? In the previously, I have chosen the point charge. Due to point charge, I find the electric field intensity. Point current element, I found the magnetic field intensity. Here also, I have taken infinite line charge, infinite length line charge. I found the electric field intensity. Similar to this, I have chosen for the magnetic fields the same kind of cause here, but it is a moving charge. It is, see, observe this, it is not at all a moving. The charge is accumulated on this line, but here the charge is moving on the line of infinite line. Okay, when there is an accumulation, electric field is existing, there is no flow. Here the flow existing. So that means, similarly, you can assume a current carrying wire I on Z axis. Suppose if we want to find magnetic field intensity at any point P, then how can we find? Let us suppose it is at rho. How can we find? How can we find? Observe this. It is the cause. Due to this, I got what? D. There also we find first D. Here in the right side means for the magnetic field I found H. Okay, the electric field strength, this is the strength. This D is represented as cos divided by 2 pi rho. But here the magnetic field strength, see, I am just simply explaining how to write the magnetic field intensity by using electric flux density. Okay, so there is a similarity between, you have to every time you have to observe, there is a similarity between D and H. There is a similarity between E and B. You have to always take this. Okay, so it is H. So H means H is equals, D is equals to what? Cos. What is the cos? Rho L. Cos divided by 2 pi rho. 2 pi rho. Rho means the radial distance. Here also H is equals to, what is the cos? Cos here is I divided by 2 pi rho. Rho is the radial distance on the point. It's very simple. Very simple. Now, you have to observe one thing here. Okay, now what is the direction? It is arrow. What is the direction? It is arrow. Now what would be the direction? Always this magnetic field will be having some direction, right? Definitely it will be having a direction because it is a vector quantity, right? So recollect the what? The Biot-Savart's law. What the Biot-Savart's law is saying? H or DH is equals to IDL cross AR divided by 4 pi R square. Because it is a vector and a vector cross product. See, if you observe this, what is the direction? The direction will be having what the direction? The H direction. It is very important. The H direction means the magnetic field direction is equal to the current direction. What is the current direction? Ideal means the direction. Ideal represents a vector. It is a point current element is a vector. The point charge is a scalar. You have to remember that. The point current element is a vector. The point charge is a scalar. Okay. So what is the direction? DL. DL direction is nothing but the current direction. Okay. Current direction cross the radial direction. From current. From current. So this is the thing you have to remember. So if you don't know this, there is no meaning of calculating this magnetic field. The direction for the magnetic field is very important. Understand? So observe this. The H field direction is equals to the current direction cross the radial direction, AR direction. Cross, this gives you the cross product. Okay, the radial direction from the current to the point. From the current, this is important, from the current to the point. What is the point? The point of interest where we have to calculate the magnetic field. So this is the radial direction. Okay, and this is the radial direction is what? Arrow. What is this? Current direction is what? AZ. So from this, what we can write? We can find the direction also. Biot-Savart's law is giving you the magnetic field intensity due to the point current element, and also it will give you the direction. Now H direction is equals to the current direction cross the radial direction. Then what would be the, already we found the magnitude, I divided by 2 pi rho. Now what is the current direction? The current direction for this is what? The current direction for this is AZ. The current is going in this direction. Cross, what is radial direction? Radial direction from the current to the point. What is the current? This is the current to the point. From the current to the point. To the point means arrow direction. Okay. It is arrow direction. Right? It is arrow. So from this, what can I write? So this is equivalent to what? This is equivalent to, I will remove this now. This is equivalent to H is equals to I divided by 2 pi rho AZ cross arrow. AZ cross arrow. These are in the cylindrical coordinates. AZ cross arrow is the third unit vector. What is the third unit vector? A5. Okay. It is satisfying the right handedness. So no need to write a negative sign there. Okay. So this is I divided by 2 pi rho arrow. Understand? So in the electric field we found D first, and the magnetic field we found H first, and there is a similarity between the D and H. Okay. So cos divided by 2 pi rho. Here cos divided by 2 pi rho. Okay. So like this you have to compare the electric and magnetic fields and what are the causes and the what? Effect. Then how you can assume the magnetic field now? How it is? AZ cross, how the A5 direction? You know A5 direction. What is the magnetic field strength? The field strength is this much. But what will be the direction? It will be in A5 direction. Now what is the A5 direction? The A5 direction is, suppose if it is the Z axis, the A5 direction is tangential around the Z axis. Okay, tangential around the Z axis. That means the magnetic field will be like this. Understand? So it is in this direction. Okay. Suppose if it is the current, the thumb shows the current, the fingers, the clockwise advancement of the fingers shows the magnetic field. It is Ampere's right hand rule. Okay. Okay. So that means the finger shows the advancement of the clockwise advancement of the finger shows the magnetic field, and the thumb shows the current direction. Okay. So this is the H field due to the infinite length current carrying wire.